Hello everyone, my name is Roland Martinez,
And my name is Alec Tolentino.
and this video presentation will be our final documentation for our project in ECE 122 section E02 or Digital Communications Laboratory. And our project is to demodulate a PWM signal or PWM demodulation. And our instructor is Engineer Marian M. Sierra. So the basic theory in pulse chime modulation is also known as pulse width modulation or pulse length modulation, where in PWM, the sample of the message signal are used to vary the duration of the individual pulses. And the width may be varied by varying the time of occurrence of leading edge, the trailing edge, or the both edges of the pulse in accordance with the modulating wave signal. This is already conducted during our laboratory experiment in activity 2 or the PWM modulation, and we created a pulse width modulating circuit using LT-Spice. In pulse width modulation, the amplitude of the pulses is constant. In generation of pulse width modulating signal, the input amplitude signal is applied to the inverting terminal of the op-amp. So in this project, we are asked to design a pulse width demodulation circuit using LT-Spice, and the concept here is to recover the input modulating signal from the PWM input signal. So there are many types of PWM demodulation, such as PWM to PAM demodulation, and also PWM to PPM demodulation. But for this project, we choose the PWM to PAM demodulation process or technique. So for the first sample, we need to use the pulse width modulating signal as the input. And as you can see in the plot, that the expected waveforms are the following. The input signal is the modulating signal coming from the pulse width modulation circuit, and the pulse carrier is the one that carrying the modulating signal, and that creates a pulse width modulating signal, where we need to extract the modulated signal using the pulse width demodulating circuit, and the expected output is the same or similar with the modulating signal. As you can see, the modulating signal must be equal to the demodulating signal. So as I have said, there are many types of PWM demodulation, but the most common techniques are PWM to PAM pulse width demodulator circuit and PWM to PPM pulse width demodulator circuit. So to discuss the sample technique in pulse width modulation, first is the pulse width modulation circuit to pulse position demodulation, where the pulse width modulation signal is input into a ramp generator and compared together with the synchronous pulse generator, and they get into the other process and a clipper circuit. Then the output signal is processed to a low pass filter, where the demodulated signal is the output. So you can see in the sample circuit diagram that this process is from pulse width modulation to pulse position modulation. Then from there, the output of the PPM is demodulated using the PPM demodulation circuit. So in this circuit diagram, the first process is using a 555 timer as the pulse width modulation circuit main component, then process the pulse width modulating signal into the pulse position modulation circuit. And the same process but with the same component, which is 555 timer, and that produces a PPM or pulse position modulating signal. And after that, the output PPM is fed into the PPM demodulation circuit, where the demodulated output must be similar to the modulating signal. Next sample technique is the basic technique, or the pulse width modulation to pulse width demodulation, or direct demodulation. In this process, we need to input a pulse width modulating signal, and that pulse width modulating signal is fed into an integrator and hold circuit, or sample and hold circuit, and that produces a pump signal. And that pump signal is fed into the low pass filter, so that the modulated output is smoothed, and the output is must be the same with the modulating signal. So for this sample, you can see the circuit diagram where the pulse width modulation circuit is using a main component of 555 timer, and the output is a PWM output, then fed into the PWM demodulation circuit, which is almost the same with the previous demodulation circuit of the PWM to PPM demodulation technique. Hi there, my name is Roland Martinez, and this is a video demonstration of the circuit design of pulse width modulation or demodulator circuit using LT-Spice, and this video will cover the time-lapse of the design and the simulation result for the pulse width demodulator circuit. So let's get started. So this is the complete pulse width demodulator circuit, consisting of the pulse width modulator and the pulse width demodulator circuit. So in this design, use the technique that is converting from pulse width to pulse amplitude, then from pulse amplitude the demodulated signal will be extracted from the pump signal. So first is the pulse width modulator circuit. Since we already demo this simulation result, I will still show you the simulated result for the pulse width modulator. So clicking the running or the run button, so we can see the input for the pulse width modulator circuit or the modulating signal as the intelligent signal. So clicking on the VIN, you can see a sinusoidal wave by clicking the VIN. Then for additional plot plane, I will select also this sawtooth generator. So you can see the sawtooth generator. Another plot plane for the pulse or the pulses or the square wave generator. And for the pulse width modulated signal or the PWM signal is the cyan colored plot in the simulated result. Next, this simulated pulse width modulating signal will be the input for the pulse width demodulator circuit on the right side. So what we did is input this pulse width modulating signal into the sample and hold circuit for as the comparator. Then it will be extracted as pump signal. Then from that pump signal, it will be demodulated using the comparator and the RLs or the low pass filter circuit. So that modulating signal will be extracted. So we will see the exact or the almost exact the same modulating signal as a result of the demodulator circuit. So to proceed, we will remove other plots. So we will retain the modulating signal or the input signal of the pulse width modulator circuit and the pulse width modulating signal or the PWM signal that is created using the pulse width modulator circuit. And this will be the references. This is the input and this is the input for the pulse width demodulator circuit. So to find out if the extracted result is successful, we need to simulate again this circuit. We already have these two results. So clicking the pump signal, so we need to add another plane. Click this, then add plane. So zooming into this, we can see a pump signal. Then after adding the pump signal, we need to extract that using we need to extract the modulating signal of the pump signal using this sample and hold circuit and the low pass filter circuit. So after clicking the output, we can compare the original value of the or the original signal of the modulating signal with the demodulated signal. So it is already zoomed in, so we can zoom out to see the result. So from here we can already see that this modulating signal in green sinusoidal wave is almost similar or approximately similar with the extracted or demodulated signal from the pulse modulator circuit or pulse demodulator circuit. So we also observe that there are ripples on the demodulated signal since the circuit has minor errors or that results to distortion of the demodulated signal, but the circuit is successfully designed and simulated.
Hello, my name is Alec Tolentino, and today I will be demonstrating our project for ECE 122L. And for our project, we will be building a pulse width modulator demodulator. We will demodulate a PWM. So I will now proceed in building our circuit in LT Spice. So simulating the circuit, we'll now be able to simulate for the modulating signal, the PWM signal, the pump signal, and the demodulated output of the PWM signal. So, thank you. So continuing on with the presentation, I will now be discussing the activity results and simulations of our circuit. So the circuit design for our project, it consists of two different parts, which is the pulse width modulator circuit, which is on the left side, and the pulse demodulator circuit on the right side. So first we'll start with the pulse width modulator circuit. The pulse width modulator circuit we use for this project is the one which we used in activity 2. The circuit utilizes a NE555 timer circuit as a trigger for switching control. This will control the on-off state of the signal for a given frequency. Then the main output is the pulse width modulated signal, where the amplitude of the modulating signal is not varied. It is also observed that when the modulating signal is at positive polarity, the duty cycle is high, where on state if the pulse is almost at 80%. And when the modulating signal is at negative polarity, the duty cycle is low, where on state is around 20%. So next, moving on, is the pulse demodulator circuit, where we used a pump demodulator signal. So the circuit for the demodulator circuit consists of two inverters, where the first inverter is for the received PWM signal, and the second inverter is for the demodulation of the PWM signal. So the PWM demodulator circuit is based on PWM to pump demodulation technique, and the PWM signal output from the PWM modulator circuit is fed into the pump modulator circuit, then demodulated using the sample and hold circuit for covering, and fed into the low pass filter for the smoothing of the modulated output. So this, as you can see in the figure, is the pulse width modulator circuit, where it utilizes a NE555 timer, where the output is a PWM signal. Then the PWM signal is fed into the next part of our circuit, which is the pulse demodulator circuit, which consists of two inverters, which is the left side inverter is for the receiving of the PWM signal, and on the right side the inverter is for the demodulation of the pump into pump signal. So next is the PWM outputs. So it is observed that the square wave has a higher duty cycle, which is almost similar with the baseband signal that is in unipolar form. It is like the negative polarity of the baseband signal is folded to the positive plane of the plot with a small width of off state before another long on state. The discharge output signal is like a sawtooth, which represents the red line, with a small and large with irregular shaped pulses. This is due to the charging and discharging of the capacitor. The main output is the pulse width modulated signal, where the amplitude of the modulating signal is not varied. It is observed that the only varied is the width of the carrier train pulse based on the capacitor discharge from the timer, regulated using a diode. It is also observed that when the modulating signal is at positive polarity, the duty cycle is high, where on state of the pulse is almost 80%. And when the modulating signal is at negative polarity, the duty cycle is low, where on state is around 20%. Next is the PWM demodulator output. So the output for our demodulation circuit is the same as the modulating signal, but the difference is it has a few fluctuations or distortions, as we can see in the blue line. So the blue line represents the demodulated PWM signal, and the green line represents the PAM signal, which was converted from PWM to PAM signal. And as the simulations show from the figure, the demodulated signal is almost the same as the modulating signal, so therefore we were able to demodulate the PWM signal. So in conclusion, in conclusion, the modulation is the act of extracting the original information bearing signal from a modulated carrier wave. Then, the modulation is used to recover information content from the modulated carrier wave. Then there are many types of pulse width demodulator. First is the first type is to let the signal convert to PAM signal via a low pass filter and demodulation. If there are three consecutive PWM pulses close to each other, then input these pulses into the integrator and voltage threshold circuit. When the pulse appears, then it will start to integrate and produce ramp until the last pulse appears. The second type of PWM demodulation is to let the PWM signal convert to PPM, or pulse position modulation signal. We can obtain the PPM signal by differentiating the PWM signal. After that, it will produce a negative edge PPM pulse at the positive edge of the PWM pulse until the end of the negative edge PWM pulse. At the same time, reset a positive edge pulse until the period of the pulse terminated, which is the PPM. And another type of PWM demodulator is the product detector. If we let the PWM signal and carrier signal input to the product detector, meanwhile, we let the PWM signal and carrier signal to be positive or negative simultaneously. Then the output terminal of the product detector will receive a pulse signal VA and send this signal to the low pass filter to obtain the demodulated PWM signal. So this concludes our presentation for our project. Thank you.
Thank you.